Good morning, guys. Okay, so a few things. I want to address today a handful of homework problems from last week's set that we really didn't get to talk about. We did get to talk about slope and linear functions just a tiny bit on Thursday, but because so much of Tuesday's class was eaten up by syllabus work, I know we really didn't get the time we should have had on that content. So I'm going to start today by letting you know that I'm extending the slope and linear functions homework from last week to next week. Let me turn on my screen share. We'll move over to the document camera. I want to go ahead and make that change now because it's different from my other sections. I don't want to forget, but then we will get started. Here we go. All right, so linear functions and slope. We are going to change the date. I'm going to push that to next week. So that will be due along with the next homework set next week. And we will talk about it today. So today is the 12th. And that will be pushed to the 19th. Quiz 1 also had some stuff like that in there, so I'll go ahead and push that to the 19th. And if you need an extra attempt on Quiz 1 because you burned all of your attempts trying to get that done, even though we hadn't really gone through the lecture material, I totally understand. Just let me know, and I'll give an extra attempt on Quiz 1. The homework that's going to open up for this week, we have homeworks 4, 5, and 6. They're on linear functions, linear models, and regression, and absolute value equations and inequalities. It's going to be a nice continuation of linear function stuff. So I think that these work well together. Those will all be due next Tuesday. That's the 19th. And they are opening up after class today. All right, so we'll make these changes and then we can get rolling. There we go. All right. So yeah, I want to go back to linear functions a little bit, where we kind of left off last week. We were moving a little fast, and talk about linear functions and slope a little bit more. Specifically, I want to make this connection to average rate of change for a function. So let's get this screen share on. I'll ask that you leave it maximized, please. If you do have any questions about syllabus stuff or any first day sort of stuff from last week, I know that some people may have added, and it is possible that today is your first day. I'll remind you that you can go to Canvas for our class here, go to announcements, and you can find the video recordings from both of our lectures last week. So if you want to go back and watch last Tuesday's lecture, that's the one that has all the syllabus explanations in it, how to get into my math lab, all the little things you need to know for the class. You can click this link. And if you want to see our discussion on domains, ranges, function notation, and linear functions and slope that we got started on Thursday, that's this other link. So it'll always be in the announcement section in Canvas here. You can always go back and rewatch those. Another thing, if you don't mind, please go ahead and download this PDF, the MAC1105 Activity 1 PDF from today's announcement. I'm going to set an alarm, and at the end of class, we're going to spend the last 15 minutes working on this. And it's an in-class activity, so it's something that we have to do like while we're here. I'll set an alarm for the last few minutes of class to make sure that we get to it. All righty, there we go. So let's get rolling. Okay, so first a couple announcements. Homework 3 from last week is extended to next Tuesday. And then, of course, there's the homework set that's going to open up for this week. So just to give you guys a picture here. Why isn't this wanting to play ball? There it is. All right. So homework 3 was originally going to be due with homeworks 1 and 2. That would have been due today at the start of class. But I decided to extend homework 3 and quiz 1. You'll see those new due dates are over here, 1/19, 1/19. That's the start of class next Tuesday. So this will be, think of this as something you can continue working on through this week. Then the new homeworks that are opening up for this week are homeworks 4, 5, and 6. Those are all going to open today at the end of class, and they will be due next Tuesday at the start of class on the 19th at 9:30. And also quiz 2, that's our second quiz. That's going to be opening today at the end of class and due at the start of class next week. And that's always the pattern. Again, for folks who may have added or who are new to the class, the way I always do this is I open up the homework on the first day of the week as soon as class ends, and then you have all week to work on it. It's due at the start of class the next first day of the week. All right. So today, we're going to continue talking about linear functions slope and average rates of change. My wife's alarm is going off here. I have to get up and grab that. I'm sorry, guys. Okay. So last Thursday, we were able to talk about the 3 different forms of a linear equation. We have the slope-intercept form, which is the one that probably most people are most familiar with. This is a line with slope m and y-intercept being the point here, 0, b. So the number b tells you the y-coordinate of the y-intercept, the number m tells you the slope, and this formula tells you how to get out a given y value associated with any particular x value. We also have the standard form and the point slope form. The point slope form is the one I would most like you guys to start getting comfortable with. It can be written 2 ways, either like this or like this. I think in our 1033 classes, they teach it like this. In pretty much every other algebra or calculus textbook, you'll see it written like this. They're the same thing, right? If you just add this y0 term over to this side, you get this second form. But this is a line with slope m. And any point on the line x0, y0. So if I tell you the slope and I tell you any point on the line, doesn't have to be the y-intercept, you can write down the point slope form of that line. This is nice because a lot of times you do have some point on the line that isn't the y-intercept. You have some point on the line besides the y-intercept and the slope, and you want to write down the equation. Oftentimes I'll see students try to work back and figure out the y-intercept from that bit of information. And that is possible, but it's extra work that isn't necessary when you can just use this formula to write things down. So think of this as a more grown-up or more general form of slope-intercept. It's your friend. We really do want to get comfy with this, especially if you intend on taking calculus. And then the last form here is the standard form, which is a little bit misnamed. ax plus by equals c. They call this the standard form of a linear equation, but we never really work with it. It doesn't really have any utility. The numbers a and b don't really tell me anything right away about the line. Neither does the number c. So we won't really mess with this guy a whole lot, but you should recognize that if you see something written like this, where a, b, and c are just any numbers, like 2x plus 5y equals -7, that is a linear equation in standard form. Okay, so this is all quick review. We also talked a little bit about slope last time. To find the slope of a line connecting two points, say x0, y0, and x1, y1, we calculate what's called we always label it as m. M is the letter that we pretty much always use for slope. And people like to refer to this as the rise over the run. All right, so you take the change in y values, and that's what we call the rise, divided by the change in the x values, and that's what we call the run. So upstairs, you're going to subtract the y values, y1 minus y0, and downstairs, you're going to subtract the x values, x1 minus x0. And there's a picture that goes along with this. Maybe over here I have the point x1, y1. And maybe up here I have the point x0, y0. And the idea of the rise over the run is that y1 minus y0 is this height, and x1 minus x0 is this horizontal distance. So that rise over that run will give you the slope of the line joining these 2 points. That's the picture that goes with this. A quick reminder, everything I put on the document camera should go into your notes. So this is where we left off last time. And we said, yeah, sure, we can find the equation of any line joining any 2 points. Or if you tell me any one point on the line and the slope, I can find that equation. Let's play around with that just a little bit. I'd like to do one or two quick examples. So let's say I want to find the equation of the line connecting the points, the 2 points, -1, 2, and 3, 5. So remember, I'll always put EG before we do an example problem. That's how you can tell we're about to start an example problem. This is a problem that you may see on a test or in a homework set once we get a little deeper into the linear function stuff. How would I get started on this? Can anybody give me a recommendation? What sort of things do I need to find the equation of this line? Yeah, remember you can hold down spacebar to talk, or you can type into chat. Tina suggests that we find the slope. I think that's really good. Yeah, that's perfect. So let's find that slope. Matthew's on top of the slope as well. So first we find the slope. That's going to be y1 minus y0 over x1 minus x0. And it's my choice how I want to label these points. I could call this x1, y1, and this x0, y0. As long as the 1s go together and the 0s go together, you'll be safe. Let's do it like this. call this one x1, y1, call this one x0, y0. So then if I follow this formula, y1 minus y0 is 2 minus 5. And x1 minus x0 is -1 minus 3. So 2 minus 5, that's -3. And downstairs, -1 minus 3 is -4. So I end up with -3 over -4, which is the same as positive 3/4, right? A negative over a negative, that's a positive number. And now I have some choices. You'll notice I don't know the y-intercept, right? The y-intercept is not immediately obvious from the problem. So the best way to proceed from here would be to use the point slope formula. And that's that equation that I gave us on the previous page, y minus y0 equals m times x minus x0. And since I've already labeled this point as x0, y0, I might as well use those here. M is the number we just calculated, 3/4. So we get that y minus 5, that's y0, is equal to m, which is 3/4, times x minus x0. Well, that's going to be x minus 3. And this is good. You can stop here. All right, you're done. You have now the equation of this line. That is the equation of this line. If you want to, you can put this into the form y equals mx plus b. You can put this into the slope-intercept form to see what that y-intercept is. First, you distribute the 3/4. 3/4 times 3 is 9/4. Now remember, 3/4 times 3 is the same as 3/4 times 3 over 1, which is 3 times 3. That's 9 over 4 times 1, which is 4. Put that off to the side there. And then we have to add the 5 over. So we'll have y equals 3/4 x minus 9/4 plus 5. And again, I have some arithmetic I need to do. Negative 9/4 plus 5 . If I don't have a calculator, how do I add these things? How do I add the fraction 9/4 to the whole number 5?
You got to change it to a common denominator.
Yeah, I need to write these both as fractions with the same denominator. And the way to write 5 as a fraction with denominator 4 is as 20 over 4. I multiply by 4 over 4, and 4 times 5 is 20. So this is negative 9/4 plus 20/4. And now we can just add the numerators. So negative 9 plus 20 is positive 11. So this is 11/4. So our final answer here, if we wanted this in the form y equals mx plus b, would be y equals 3/4 x plus 11 over 4. And I think we'd all agree that if we'd drawn a picture or even used a graphing calculator or something like that to graph this line, or even if there was some way to like cheat and graph the line before writing down the equation, we wouldn't have been able to guess this, right? Looking at that graph, we wouldn't be able to guess that that y-intercept is exactly 11 over 4. How would you know it's 11 over 4 and not 12 over 4 or 10 over 4? It would just be this tiny little difference in the picture that we wouldn't be able to detect by eyes. So this is one of the reasons the algebra process is so important. all of this has been done before. I'm sure none of this is new to you guys, maybe just some refreshers on formulas and methods of calculation, but something that maybe is new is this concept called average rate of change. So if there are not any questions on this example, I would like to talk next about that. Are there any questions we'd like to ask about how we found the equation of this line? Anything that we'd like to look at more carefully or anything along those lines? Okay, then I am going to move forwards. Average rates of change were in homework 3, but we didn't get to them last week. That's why we're extending homework 3. Here's the idea. You have some function, f of x, not necessarily a linear function. Maybe its graph looks like this. And you want to know between one point on the function and another point on the graph of the function, how much the function has grown or shrunk over that interval. So remember, we think of the outputs here, the y values, as outputs, f of x, the input values we call x. And maybe I'll call this guy x0, and I'll call this guy x1. Then the point on the graph at x0, of course, has x coordinate x0, and the y coordinate there would be f of x0, because we're along the graph f of x. And similarly over here, the point on the graph of f of x above x1 is x1 comma f of x1. Now some people would choose to call this y0. That's fine. If you want to do that, just remember that it is f of x0. And similarly, some people would choose to call this y1. The thing we call the average rate of change for that function is the slope of the line connecting these points. Okay. Now a line like this, the blue dotted line you see here, is called a secant line. This is called the secant line for f of x from x equals x0 to x equals x1. And the definition of the average rate of change for f of x from x equals x0 to x equals x1 is the slope of the secant line. Which is going to be, here, what order did I write it in previously? y0 minus y1 or y1 minus y0? We'll be consistent here. y1 minus y0. y1 minus y0 over x1 minus x0. Which can also be written in this function notation as f of x1 minus f of x0, all divided by x1 minus x0. And this is not multiplication, right? This is not f times x1. This is not f times x0. These are the outputs from the function f associated with the input x1 and the output from the function f associated with the input x0. Remember, we talked about f as being like a little monster, and the parentheses are like its little mouth. So this is what the function outputs when you feed it the food x1. And this is what the function outputs when you feed it the food x0. Totally different from multiplication. They just happen to look similar. A neat thing to think about here is what we call units. If you've ever taken a chemistry or a physics class, you've no doubt discussed units and dimensional analysis. The units of this expression are the units of f of x divided by the units of x. And what I mean by units are the thing that's being measured. So for example, if f of x measures distance in meters and x measures time in seconds, then the average rate of change for f of x is measured in the units of f of x, which is meters, divided by the units of x, which is seconds, which is the same as, sometimes we call this meters per second. And you have a handful of homework problems that ask you to calculate the average rate of change for a given function. And you'll see them including things like boxes per year or dollars per bicycle, that sort of thing. Those are coming from the units of the output divided by the units of the input. This is called dimensional analysis. And the notation you see me using here, where I put the units in brackets like this, is a pretty common notation. MIT started it back in the 80s, and it's taken hold everywhere in the academic community. So writing your units in parentheses like this can be a nice thing to do. All right, let's look at an example problem from that homework set. Let me see if I can come back here. We'll work a couple of those before we move on. There were one or two that I got emails about, so I just wanted to clarify. I think, oh, where'd we go? Here we are. Preview. Numbers 29 and 30, I think I got a couple of emails about, so I just wanted to work through at least one of those as an example here in class today. Right. So here you see it says the revenue in thousands of dollars from producing X units of an item. So maybe, they're making bicycles or loaves of bread or dog collars or something. From producing X things is modeled by the function r of x equals 11x minus 0.001 x squared. They want to find the average rate of change as x changes from 1002 to 1005. So I'm going to tab back over to the document camera. I'll bring this over here so you can still kind of see it. All right. So they want us to find, I should say what this is, right? This is homework 3, problem number 29. We're working as an example. Find the average rate of change, and you'll see me abbreviate average rate of change as AROC, for the revenue function, which is R of X equals 11X minus 0.001 X squared, as X changes from X equals 1002 to X equals 1005. Now, we don't necessarily know what the graph of this function looks like. All right, we will talk about how to graph functions like these next week when we talk about quadratics, because this happens to be a quadratic function. But this function doesn't have any one particular slope. It's a curve. It's curvy. It's not straight. So remember, linear functions are those that have a constant rate of change. The rate of change is always the same. That's the slope at any given point. This guy's slope is changing all the time. So we have to look at these two particular points, the point associated with X equals 1002 and the point associated with X equals 1005. In other words, we're going to use the formula that we discussed on the previous page. So the average rate of change should be R of 1005 minus R of 1002 over 1005 minus 1002. In other words, we're finding the slope between the points 1002 comma R of 1002 and 1005 comma R of 1005. So clearly what I need is these numbers, right? R of 1002 and R of 1005. However you choose to think about it, as coming from this formula or thinking of it as the slope between these points, we need to know what is R of 1002, what is R of 1005. R of 1002 is what you get when you plug 1002 in for X in the formula for R of X. It's 11 times 1002 minus 0.001 times 1002 all squared. And this is where your calculator will come in handy. And I have an emulator, so I can show you how to do all the calculator things here. Oh, wait, is this not going to work? Please run. Blocked by administrator. All right, I can probably find one. I thought I had another one. This is that same one, isn't it? Yeah, okay. I'll find a different one here. One of these will work. Let's see what we got. Here we go. All right, looks good. So we want R of 1002. That means we need 11 times 1002 minus 0.01 times 1002 squared. I'm going to enter this exactly as it appears here into my calculator. The parentheses are all important. So please, when you do these problems, anytime you're plugging a number into a function, like we did here, do so in parentheses. Anytime you're plugging an expression into a function, do so in parentheses. These parentheses are all important. So let me see if I can tuck this. Yeah, okay. I need 11. Whoop, come on. Oh, please work. Please, please work. God damn it. Screenshot, why aren't you working? Oh, here, I just probably have to hit play. All right. No, on, no, damn. All right, we'll try another one. Here we go. This one looks good. Okay. So we need 11. No. Damn, all of these things are like this, huh? Preferences. It has to be one phase. Worst case scenario, I can put my physical calculator right here in the browser. I have one saved on this computer, but for whatever reason, the administrative changes don't allow me to use it anymore. Yes, please. This is where we were. Maybe I have to agree to the TOS. Is that it? All right. Am I missing something here? Please no. Restore the local browsers. Export the wrong manager, please. Do not. 3. How it works. I'll leave this over here and try to sort this out on this side. Only store on your local browser. So what am I missing here? Screen code. Please register the login and access this full features. What am I missing? God damn it. All right, I'm just going to grab my physical calculator. I'll hold it under the thing for you. Sorry about this. So here's how we're going to do this calculation. I'll get an emulator working here soon. Let's see, can we see this? God, that's crap. Okay. So we're going to enter this as 11 times parentheses. It's all garbage, isn't it? 11 times parentheses 1002 close parentheses minus 0.001 parentheses 1002 close parentheses, and then this little button right here is how you get into the exponent. Type caret and then a square. And here's our number. So this is 10,017.996. And the other value we needed was R of 1005, which is 11 times 1005 minus 0.001 times 1005 squared. And we'll calculate that the same sort of way. We'll type here 11 parentheses 1005 minus 0.001 times parentheses 1005 all squared. And that's 10,044. 10,10044.975. So now we're ready to plug these things in to our formula. So Matthew, the problem asked us to find the average rate of change for the function r of x equals 11x minus 0.001 x squared from 1002 to 1005. And we said, okay, that's this slope. That's the slope between the points 1002, comma, r of 1002, and 1005, comma, r of 1005. And the way we calculate that slope is using this formula. Right, the average rate of change formula from the previous page. Now that we have these numbers, we can plug them in. So here's our little bit of side work to find those numbers. And the average rate of change is going to be R of 1005, which is this number, 10044.975, minus R of 1002, which is 10017.996, all divided by 1005 minus 1002. The order of subtraction doesn't matter as long as you're consistent top to bottom, just like we talked about with the calculation of slope the other day. As long as you have whatever's here, here, and whatever's here, here, you could flip them over as long as you flip both the top and the bottom. So just make sure that you're subtracting in the same order in the top as you are in the bottom. Now, if I do this difference, I'll put it over here. $10,044.975. So you can see it. 10,044.975 minus 10,017.996. Here's our numerator, 26.979. Divided by 1005 minus 1002, well, that's just 3. And I really suggest calculating the top and bottom separately like I did here. Otherwise, you have to be very careful with parentheses. Remember, fractions are grouping symbols. We really have to think of the top and bottom as being in parentheses. So if you wanted to type this whole thing in at once, make sure you put the top and bottom in parens. But my suggestion is just do one step at a time. Calculate the top, calculate the bottom. And now we can divide that previous answer by 3, and that will give us 8.993. And this was the change in revenue as they went from manufacturing 1002 gadgets to 1005 gadgets. So we would say that the revenue went up by $8.993 per item. Because remember, the things being measured here, the top, these are outputs from the revenue function. Revenue is the amount of money coming in. So that's being measured in dollars. And downstairs, the inputs are the number of items we're manufacturing. So we went from making 1002 items to making 1005 items. And overall, our revenue has increased. Our revenue has increased by $8.993 per item. All right, I apologize for the clunky calculator stuff. I promise I'll contact Santa Fe IT and get them to give me permission to run my emulator. I don't know why it's not running. But this is really how we find average rates of change. You'll see a lot of problems like this in homework 3 and 4. The new homework for this week will have some similar word problems like these. Okay, doing good on time. So we'll get rid of this, but I would like to come back to H. Pearson here. Close this. So yeah, sadly, regression is another big topic for this week. And then we need to talk about absolute value equations, inequalities, and graphs. So let's talk a little bit about linear functions and equations. I think we all have the basics of these down, but we can work a handful of problems here. And I think everybody would probably appreciate if I just work problems from the homework. So let's do that. Let me pop this open. We'll look at a few problems from the first new homework set this week. All right. So they've given us an equation or a graph, and they want us to find the equation. I'll do one like that, but let me jump to something a little tougher. Parallel to this. Okay, so we'll talk about parallel and perpendicular lines. So that first problem is actually really similar to the first example we worked today, where we said, find the equation of the line passing through these 2 points. It's just that they're working from a picture instead of working from the words. So this is analogous to homework 4, problem 1. We want to find the equation of the line graphed below. Now those points are randomized in the homework, so it won't help that I work the particular one there. So I'll go ahead and make up some values for these points. Let's have one of them be over here at -2, -1. And let's have another one be over here at 4, call this 3. So I'd like to find the equation of the line between these 2 points. The easiest way to do these is with the point slope formula, which means you need 2 things. You need a point and you need a slope. So we'll calculate first the slope. Again, you can choose to label these however you want. I'll call this x1, y1, and I'll call this x0, y0. But you could swap those around if you wanted. Zoom in here so you can see a little better. We know that this is going to be y1 minus y0 over x1 minus x0, which is 3 minus -1 divided by 4 minus -2. 3 minus -1 is 3 plus 1 is 4. 4 minus -2 is 4 plus 2 is 8. And 4 over 8, that's the same as 1/2. So the slope here is 1/2. And then I can use my point slope formula. This really is a nice tool because you see, I can't really tell what that y-intercept is. Maybe my picture is just bad and the y-intercept is 0. Or maybe my picture is correct and the y-intercept is some positive number just smaller than 1. I'm curious about that question, Brooke. So walk me through what you're thinking there. Did I? Oh, yeah, 4 minus -2 isn't 8, is it? It's 6. Yeah, thank you, thank you. Yes.
Yeah.
Sorry. So the numerator here is indeed 4. 3 minus -1 is 4. But 4 minus -2, that's 4 plus 2 is 6. Yeah, so here, this slope is indeed 2/3. I appreciate you catching that just before it ran off and ruined the problem. That's very sweet of you. Okay, so now our point slope formula says we can get the equation of this line as y minus y0 equals m times x minus x0. I can use this point that I've labeled as x0, y0. And of course, this number here is m. So that's y minus -1 equals m, which is 2/3 times x minus -2. And again, this business that I'm using with parentheses every time I plug into an expression, really you should do the same. We can clean this up a little bit. That's y plus 1 equals 2/3 times x plus 2. And there's no need to put this into y equals mx plus b unless the problem explicitly asks for it, but it's not a bad idea to practice the algebra. So if I wanted to put this into the point or a slope-intercept form, I would distribute the 2/3. So I get y plus 1 equals 2/3 x plus 2 times 2/3 is 4/3. So here I'm distributing this. And then I can subtract 1 from both sides. So I get y equals 2/3 x plus 4/3 minus 1. And again, practicing with fractions is something that we're just going to have to grapple with in this class. So I encourage you guys to put down the calculator when it comes to doing these little things and see if you can't just reason your way through them. 1 is the same as 3/3. So 4/3 minus 3/3 is 1/3. So we have here y equals 2/3 x plus 1/3. Right, and this is our slope-intercept form. Any questions on how we found the equation of this line or why we did any of these steps? Okay. Let's grab one more problem from here, and then we're going to shift into our activity for today. The activity is very easy, I promise. It's nothing stressful. So they say find a linear function parallel to the given line passing through the specified point. So we need to talk about what makes two lines parallel and what makes two lines perpendicular. An important fact in mathematics is called a theorem. Two lines are parallel if and only if they have the same slope. And two lines are perpendicular if and only if their slopes are opposite reciprocals. So parallel, the two lines will have slope m1 and m2, and they'll be equal. Perpendicular, the two lines will have slopes m1 and m2 satisfying an expression like this. If the two slopes are equal, those lines are parallel. If the slopes are opposite, that means negative. Reciprocal, that means flipped over. Then that's how you know that they are perpendicular. All right. And the picture, of course, parallel lines, they never touch. So two parallel lines might look something like this. And you see they have the same slope. You go over some amount, you go up some amount for the one line. That's the same amount you have to go over and up to stay on the other line. Same slope. Perpendicular lines, what perpendicular means is they intersect at a 90-degree angle. So for example, the x-axis and the y-axis, those are perpendicular lines. But you can also have other perpendicular lines, like this fellow is perpendicular to this fellow. Now here, both of these slopes in the parallel line, these guys both look to have slope like 1. Here, this guy's slope looks like maybe 1/2. Call this line, we'll just do it like this. We'll say this guy has slope here. 1 equals positive 1/2. And this guy, his slope is clearly negative. And if he's going to be perpendicular to that guy, then he would have to be the negative reciprocal of this, which would be -2. And the fact that they're perpendicular means that they meet in a 90-degree angle. Not any two lines that cross are perpendicular. They have to cross at exactly 90 degrees. Okay. So this next problem is akin to homework 4, question 10. We're working it as an example. We'd like to find, what did they say? Find an equation for a linear function parallel. Find the linear function parallel to, I'll make up my own stats here, y equals 3x minus 2, passing through the point, how's about -1, 7. All right, so I have a line, y equals 3x minus 2, and a point, -1, 7. What I want to do is find another line, so it's going to be another expression looking something like this, that is parallel to this guy, but passes through this point. So let's draw the picture. Always worthwhile to draw the picture. Line 3x minus 2 looks something like this. It has a steep positive slope. All right, the slope is 3, meaning every time I go over 1, I go up 3. So if this is 1 here, then this point will have been 3 up. That should be 1 here. So this point is 1, 1. My y-intercept down here is 0, -2. I want to find another line parallel to that one, but that goes through the point -1, 7, which is way up here. So I need two things to find my line. I need a point on that line and the slope of that line. My line is supposed to be parallel to this line. So my line must have slope m equals 3. Because this line has slope m equals 3. And two lines are parallel if and only if their slopes are the same. And that's it. This is really all we need, because the point, now we can use our point slope. Y minus y0 equals m times x minus x0, with this point as x0, y0, because my line has to go through this point, and this slope, because my line has to be parallel to this line. So my line would be y minus 7 equals 3 times x minus -1. And again, if we wanted to, we could put this into the slope-intercept form. We could put this into the form y equals mx plus b, but it's not necessary. Any questions on how we did this, or how we would find a perpendicular line if we needed one? Okay. So these relationships between parallel and perpendicular lines, I'll just zoom out a little bit so you can see both. These relationships between parallel and perpendicular lines are important. Two lines are parallel if and only if they have the same slope. Two lines are perpendicular if and only if their slopes are opposite reciprocals. I'd like to move now to our in-class activity. So the last 15 minutes here, we're going to work on this in-class activity, which means I'm going to be assigning you guys to breakout rooms. I'll ask that you stay patient with this. I'm going to assign automatically. We have how many? 26 people here. So I'm going to make, let's do 7, 26, not divisible by that. I'm definitely not going to go that high. So we'll just have a few people distributed unevenly. We're going to create 6 breakout rooms, and you guys are going to be assigned automatically to those rooms. I'd like you to open up the PDF that I attached to our announcement earlier today. Where was it? Here. Open up this PDF. It looks like this. And we're going to work through these problems together. All right, I want you guys in your breakout rooms to work through these problems together. Now you can work on your own page, or if you've been able to print this page, you can work on what you've printed, but I want everybody to have a say in the problem solving, and I'm going to come in and check in on you guys and try to talk to everybody a little bit. All right, so I'm going to assign you to breakout rooms now. Please go ahead and open up this PDF, and we will talk a little bit about these problems. We haven't had time really to get to this increasing, decreasing stuff. But I will, let's just worry about page 1 here. Sorry, this is an old activity. 1105 has changed a little bit. So worry just about page 1. Don't worry about page 2. We're just going to make sure we're all comfy with the interval notation and the shading on the number line. This other stuff we'll talk about this some other time. Don't worry about page 2. Alrighty, so there we go. Let's do it. So you've been invited to join. Please go ahead and accept those, and then I will move through the rooms working on these problems with you. All right. Okay, Emily, Jacob, and Andrew, how are you guys doing today?
Pretty good.
Is everybody able to view the activity here?
Yep.
I'm pulling it up right now.
Yeah, I'm good.
All right, let's go ahead and pull that up. I'm going to turn on my screen share so we can talk together about some of these. Can you guys all see this okay?
Yes.
All right, feel free to move it around. You can unmaximize the screen share so you can view the PDF on your own. But just talk through me a little bit. So if I wanted to, in interval notation, express, for example, in B here, all numbers greater than 3, what would that look like? What would the endpoints of the interval be? And what kind of delimiters would I use, brackets or parentheses?
Wouldn't 3 be in brackets and then the rest be in parentheses?
So 3 is definitely going to be one of our endpoints. And I think if we want to figure out exactly how to write this set in interval notation, the easiest way to do it would be to draw the interval, right? So we look on our number line here. And since 3 is the only number that's specified, I'll just plop him any old spot. If I want all the numbers that are greater than 3, am I talking about stuff to the left over here or stuff to the right over here?
To the right.
Alright.
Very good. Yeah, definitely to the right. So I'm interested in all the numbers that are bigger than 3. That means I'm interested in everything over here to the right of 3. What about 3 itself? Is 3 greater than 3?
No.
Yeah, just like I'm not taller than myself, 3 is not greater than 3. So if I had to draw this using the number line notation we were using last time, it would look like this, right? Not 3, but everything that's bigger than 3, everything that's to the right of 3. So what does my interval notation look like here?
It would be both in parentheses, so like parentheses 3 and then infinity close parentheses.
Perfect. Yeah, we always use the paren on the infinity symbol, and then we use a paren on the 3 here as well, because 3 is not included in this set, right? 3 is not itself greater than 3. So this is perfect for part B. I'd like you guys to work through the rest of the things in problem 1, and I would like it if everybody talk a little bit. I know that this breakout room stuff on Zoom is not anybody's favorite thing to do, but it's important that you just talk a little bit with each other about these. So please, everybody pull this up. And talk through all parts A through F of problem 1 and problem 2 there, parts A through E in problem 2. Don't worry about the reverse page where you've got the function graphed on that thing. We won't talk about that today. Just worry about page 1. I'll come through and bug you about one more of these before we sign out, okay?
Thank you.
All right. Hey guys, how are we all doing today?
Good.
Good, good. Okay, I know this breakout room stuff can feel a little bit awkward. I appreciate you guys being patient. Has everybody been able to pull up that PDF? Can you all see these problems?
Yes.
Yes.
All right, I'd like to talk through one of them with you now, and then I'm going to come around one more time to bug you before class ends. You only need to worry about the front page. Don't worry about the second page with the graph of the function. So just worry about problems 1 and 2. I'd like you guys to work together to complete A through F in problem 1 and A through E in problem 2. Is there one of these in problem 1 that looks most challenging, one that you guys would most like to talk about?
Can we do A?
So one of the big challenges in this class is getting to a place where we can take the words into the mathematics notation. So let me tab over here to my .cam. Tab over here to the .cam. Part A is just asking for all real numbers. And we want to put this in interval notation. Now the trick to all of these, parts A through F in problem 1, is to draw your number line and then shade the parts that you want. A is a little bit silly because there's no endpoint given, right? We want everything. We want the whole real line. So is anybody familiar with how you can express the whole real line in interval notation?
We talked about negative infinity and positive infinity, but we weren't sure if that one was right.
That's good. Yeah, this goes all the way off in this direction to negative infinity, and this goes all the way off in this direction to positive infinity. I want everything. And then when it comes to the infinity symbol, we always use the open parentheses because you can't actually get there. Infinity isn't actually a number. So the idea of like getting to infinity and including that in my set doesn't really make sense. So I would never use a hard bracket. I'll always use the soft parentheses. So definitely all real numbers, you're 100% correct, is negative infinity to infinity. Is there another one that we'd like to talk about real quick before I move to the next room?
I think we're good after that.
Okay, yep, spend some time, work on problems 1 and 2. Don't worry about the reverse page. I'll come back one more time to bug you before the class is over. Okay.
Right, you see it?
Alrighty. Were you guys able to get the PDF open? Are you able to see everything?
Yeah.
Is
Yes.
anybody having any trouble viewing the document?
No.
No.
So we're just going to work problems 1 and 2 today. Don't worry about the reverse side of the page with the function graph. You don't need to fret about that today. But on that first problem where we're writing sets in interval notation, is there anything that you guys would like to look at together? Anything that feels a little bit weird? Any of these that you guys, let's pick one that we'd like to work together.
I think F is the hardest one but
Yeah, F is certainly the hardest one here. Would we like to jump straight to that?
Yeah.
All
That's
right.
cool.
So we want all real numbers except for 2 and 3. The trick for all these problems, I think, is to draw the line and then shade the set you're interested in. So maybe I'll plop 2 down right here, and I'll plop 3 down right here. I want everything except for those 2, which means I want everything to the left of 2, everything between 2 and 3, and everything to the right of 3. So I have these 3 regions. I don't want 2 itself, so I need to chop him out. And I don't want 3 itself, so I need to chop him out. Is everybody following how I came up with this little diagram?
yes.
All right. So if I want everything to the left of 2, but not including 2 itself, what is this region over here? How would I express just this part in interval notation?
Negative infinity to 2.
Good. Yeah, that's negative infinity to 2. I always use an open paren on the infinity symbol, never a bracket. What should I use at the 2?
Parentheses.
Just a regular
Good.
parenthesis.
Yeah, an open parentheses again, because if I used a bracket, that would mean I'm including 2, but I don't want 2 in my set. I want everything except for 2 and 3. So this first chunk over here is this. What about this middle chunk? What is that?
X.
Well, so if I wanted to express this in interval notation, what would be my left endpoint and what would be my right endpoint?
2 and 3.
Yeah, right. This is everything between 2 and 3. And again, I don't want to include 2. So I'm going to use a parentheses over here. What about the 3? Should I use a paren or a bracket there?
A parentheses.
Yeah, parentheses again, the same sort of logic, right? Remember the hard bracket, the square bracket means I want to include that in my set. And the soft parentheses here means I don't want to include that in my set. And then finally, what is this guy over here?
3 into infinity.
Good. This is the set 3 to infinity. And again, parentheses on infinity, because we never include him, and parentheses on the 3, because we don't want to include him. And then we would join these together with union symbols, right? So this set, in words, all real numbers except for 2 and 3, is this set in interval notation. And doing this sort of thing, figuring out how to write the set all real numbers except for a couple particular ones, is going to be really important later when we talk about domains of rational functions, because that's exactly how those things look. So this is a great example. I'd like you guys to continue working. Make sure you get all of A through F in problem 1 done and discuss them until you all agree on your solutions. And then similarly with problem 2. Is there anything I can help you guys with before I bounce to the next room?
I don't think so.
Alrighty then, I'll come back and bug you all one more time.
Thank you.
Hey, Kendra, Charles, Gabriel, how are things going? Or Gabriella, I'm sorry. Are you guys all able to open the document?
Yeah, Yeah, things are going pretty good.
Okay, let's take a look at one of the parts of problem one. Is there? I'm sorry. Is there any one piece here in problem one that you guys would like to look at together? Anything that's got a little bit of uncertainty around it? Maybe I can ask you guys about part C. How are we working on part C? Any ideas for what we could write here for interval notation?
Parentheses, 1, 7, and then the bracket.
Very good. Yeah, that's perfect. Was that Charles?
Yes, sir.
How did you arrive at that, Charles? That's exactly correct. Can you share with me a little bit what you're thinking? So what Charles said was correct. This is parentheses 3 up to 7 and then a bracket. But I'd be curious to know how you arrived at this conclusion. Or if anybody else wants to answer here, I'm just looking for a little bit of input.
So he got it because, let's see. So you use the parentheses when the numbers are not included in the brackets when they are included. So it says greater, it has to be greater than 1. So that was where they, oh, sorry. Wait, which number are we looking at?
This is, oh, greater than 1. Sorry, I wrote down the wrong thing there. Yeah.
So they have to be greater than 1. And then when it says not exceeding 7, that means 7 is included.
Good. Yeah, okay. So 1 is over here on our number line and 7 is over here on our number line. If I have to be greater than 1, that means I have to be to the right of this guy. So that's stuff like this. And yeah, since we have to be greater than 1, we don't want to include 1. Since we're not allowed to exceed 7, we're not allowed to go past 7, but 7 is allowed, right? 7 does not exceed 7 in the same way that I am not taller than myself. And then if you just take this, it's easy to shift into this, right? So this sort of
parentheses, I got it wrong.
That's okay. No, this is exactly why we do this. So it's a little bit subtle. And one of the hardest things in this class is translating the words into the math symbols. So this is the correct answer. And my recommendation, if you're having trouble coming up with exactly that, is to try sketching it on the line like this. So definitely things greater than 1 would be everything to the right of 1. But I also need them to not be greater than 7. So that means we have to be no bigger than 7 and no smaller than 1, which just leaves the stuff in between. Since 1 is not greater than 1, we would not include the 1. And since 7 does not exceed 7, that matches this criterion, so we can include the 7. So talk with yourselves and make sure you're really comfy with where this and your other answers for part 1 come from. And then I'll pull everybody back into the room and we can discuss problem 2 together in just a few minutes. All right, about 2 more minutes.
Okay.
All right.
Thank you.
Of course. Okay, Mark, Sophia, William, how are we doing? Any troubles? Was everybody able to open the document okay?
Yeah, it's pretty easy. I just needed help with F. That's pretty much it.
Okay, yeah, F is pretty sneaky here. So we want every real number except for 2 and 3. So let me turn on my screen share and I can show you guys a little bit how I go through this. These sort of sets are really important because they show up as domains of rational functions all the time. So we want all real numbers except 2 and 3. So for any problem like this, I think it's helpful to draw the number line, plop down any numbers that are obviously relevant, in this case, 2 and 3, and then try to just shade in the stuff you know you want. We know we don't want 2 and we don't want 3, but we do want everything else. So that's going to be everything that's to the left of 2, everything that's between 2 and 3. And remember, there's infinitely many numbers in here, like 2.1 and 2.9 and 2.5. So there's lots of stuff in there. And then everything that's to the right of 3. Now, I don't want 2 itself, so I need to make sure that I'm plucking these out. So I want everything up to, but not including 2. That's this paren. Then I want everything bigger than 2 and smaller than 3, everything that's strictly in between them. And I want everything that is strictly bigger than 3. So what is this leftmost set in interval notation? What is this piece? Just that piece in interval notation. Everything to the left of 2 here.
Would it be 2 and then negative infinity?
Those would be my endpoints, but we need to make sure we put them in the correct order. So negative infinity would come first because we're thinking of that as being to the left. And in our intervals, we always put the smaller thing on the left. So this guy would be negative infinity to 2, like that. We always use the open paren on the infinity symbol. Why do I use an open paren on the 2?
You're not including 2.
Very good. All right, what about these guys between 2 and 3 here? How would I write that?
Parentheses.
You write it as a union.
Yeah, we're definitely, so Sophia's correct. We're going to union this with whatever goes here. And then what is it that goes in here? Maybe maybe Sophia can follow up that. So we're going to union this with this set. What is this set in interval notation?
Parentheses 2 and 3.
Perfect. Yeah, that's exactly right. I don't use a bracket because I don't want to include 2 or 3. I want everything except for 2 and 3. But I don't want to miss the stuff that's in between 2 and 3. There's all these weird decimal numbers in here, like 2.1 and 2.5, 2.9. The square root of 5 is in there somewhere. So there's lots and lots of stuff in here that we don't want to miss. And we get that with the parentheses 2 to 3, the open interval there. And then maybe William, how would I write this set on the far right? Everything that is to the right of 3 here. How would I express that in interval notation? Oh, William, are you there? Remember, you can hold the space bar to talk. Okay, it seems like maybe we lost William. Was he here earlier, guys?
I'm not sure.
No.
Oh, I see. Well, Mark or Sophia, could either of you help me with this far right set here? What is that?
3 infinity.
Beautiful. Yeah, this we would union this with the interval 3 to infinity. All right, I have one more room to check on, then I'm going to pull us all back in together, okay?
All right, thank you.
All right, take care, guys. Thank you.
I think
Okay, nobody here. Okay, let me break. Okay, let me see here. Can we get everybody back in? Still waiting on a few folks.
So I have another class I'm supposed to be starting to join right now. Can I leave?
Yeah, you can go ahead and move. I understand we're running a little bit over time here. What I would like you guys to do, I'm going to give you credit for the activity just based on our little pop into the room discussion. So don't worry about getting credit for the activity, but please do take the time to make sure you can answer all of those questions. And if you run into any problems answering those questions in activity 1, I would really like you to come by an office hour. One of my big goals for the first 2 weeks of this class is to see everybody in an office hour at least once. So if there's anything that you have any uncertainty about at all, please come by one of my office hours this week so we can talk about it, all right? Everybody's going to get credit for the activity. Don't panic about that. We're just doing that based on the Zoom logs in the breakout rooms. Office hours, remember you can find them in Canvas. I'll turn my screen share back on here and show you. So if you go to our class in Canvas, go to the home page, you'll see links to join the office hours, Monday, Wednesday, Friday, 1 to 2, and Tuesday, Thursday from 11 to 12. If you can't make one of these, but you would like to talk to me about something, just send me a message on Canvas and I'll arrange an alternate meeting time with you. Alrighty, so we got to get moving. Next time we're going to talk about linear regression, which is a neat technique for fitting lines to data sets. And we're going to talk a little bit about solving linear equations and absolute value functions. If you have any problems getting into MML, please get those resolved immediately. You can contact me for help with that. I can bend Pearson's arm a little bit if need be. And if you have any issues at all, don't hesitate to come by an office hour or send me a message on Canvas. Alrighty, I'm going to go ahead and end our meeting here for today, guys. Continue working on that homework, and if you get stuck, please ask for help. Have a good day.